last but certainly not least, let's go ahead and talk about the central limit theorem. And in order to do that, I'm going to introduce a really simple example. So here's a little preview. So for a population, we can define a parameter such as our mean, standard deviation, mode, percent of population with a specific characteristic, right? We can then take a random sample from this population to calculate a sample statistic, which is used to estimate the population parameter, right? Our whole goal in statistics is to take a sample, a representative sample that we've picked really well, collect some information about that, and be able to use that to make an assumption about our population parameter. However, every time we take a new random sample, the statistics may change. So a big question we have in statistics is, how do I best approximate my population mean? What's the best way to approximate a population mean? So let's say, for example, my population is 3 balls, 1, 2, 3. And the parameter I'm interested in is the mean. I can go ahead and calculate the mean of my population, right? This is a really tiny population, and I find that my mean is 2. But let's go ahead first and pretend like I'm not taking my entire mean into account. Like, let's just take samples of 1 ball at a time. And to calculate the statistic, this will help us estimate the parameter if we didn't already know it. Like, we know it's 2, but pretend you know that. So let's go ahead and pick samples of size 1. So here are my possible outcomes, and here are my possible means. Now let's go ahead and write these means in a frequency table. So a mean of 1 occurs once, a mean of 2 occurs once, and a mean of 3 occurs once. I'm going to graph this frequency table. This frequency table for a mean of 1, 2, 3 has a frequency of 1, right? So 1, 2, 3, right? This is a uniform distribution. This is not very interesting, okay? And it doesn't really show us what our true population mean was. Well, let's try this again by taking samples of numbers 2, right? So, for example, if I pick 1 and 2, 1 and 1, the mean is 1. 1 and 2, the mean is 1.5. 1 and 3, the mean is 2. So I've made a list of all my possible pick outcomes. And I'm picking them with replacement. Like, I could pick 1, I put it back into the bag, and I pick 2. And here I have all of our possible means. So let's make a table of our means and the frequency in which they occur. So here I have a mean of 1, and it occurs once. A mean of 1.5, it occurs twice. A mean of 2 occurs 3 times. A mean of 3 occurs once, and a mean of 2.5 occurs twice. If I go ahead and graph this frequency table with a mean of 1, 1.5, 2, 2.5, 3, now that I've taken samples that are bigger in size, doesn't it appear that my graph has started to take on a normal curve? What do you think would happen if I got samples of size 3? My graph would get closer and closer to a normal distribution. This is found, and we can prove this using the central limit theorem. So the central limit theorem states if I keep drawing larger and larger samples from a population and calculating their means, the graph of the sample means will form a normal distribution, right? The graph approaches a normal distribution as my sample size gets larger, and the mean of this normal distribution approaches our population mean, right? We want to find our population mean. That's the goal. So here's the central limit theorem. Suppose we take many random samples of size n for a variable with any distribution. It doesn't have to be normal, but it'd be good if it was. Then we have the distribution of the means will be approximately a normal distribution for large sample sizes. So typically we want n greater than 30. And I know my example was very tiny, but typically we want a sample size greater than 30. The mean of the distribution of means approaches our population mean. So what we're doing is we're taking samples of size n, we're finding their means, we're calculating their frequency, and we're graphing the distribution of the means. The standard deviation of our distribution of means approaches sigma over the square root of our sample size, as long as we have large sample sizes, and standard deviation sigma is the standard deviation of the population. So if I had my original distribution and I take bigger and bigger sample means, my distribution gets tighter and tighter and tighter. And that's going to be the same for a uniform distribution, a distribution that's skewed, or a normal distribution. So the central limit theorem thing works for all distributions. So let's say you're a middle school principal and your 100 8th graders are about to take a national standardized test, and the test is designed so the mean score is 400 and a standard deviation of 70. I want to assume my scores are normally distributed. What's the likelihood that one of my 8th graders selected at random will score below a 375 on the exam? So we can calculate this. This is just one student. So I've got z equals 375 minus 400 over 70. That gives me negative 0.357. So I go to my z table and I find a z table value of 0.3594. So there's a 36% chance that one of my students will score below a 375 on the exam. Now, the real question is, let's say I want to know what the likelihood that all of my 100 8th graders have a mean score below 375. This is when we use the central limit theorem. A good hint to when you're going to need to use the central limit theorem is it will give you an n. It will give you a sample size. So now I know z equals x minus mu over my standard deviation divided by the square root of n. So I've got 375 minus 400 over 70 divided by the square root of 100, and I get a z-score of negative 3.57. When I go to the z-table, this is really unlikely to occur. I get a z-table value of 0.0001. So there's a 0.01% chance that the mean of my 100 8th grade students is below 375, right? This is really different from the probability that I'd have one student who scored below a 375, which was 36%. So the central limit theorem allows us to say something about the mean of a group if we know our mean and the standard deviation of the entire population. If we don't know the standard deviation of the entire population, that's something we're going to be talking about in Chapter 7.